like introduction to crashworthiness simulation, right? So what are the prerequisites? So before we start anything, so there are certain prerequisites which are required. Okay, so like what are the prerequisites? So the prerequisites is, so you should have knowledge about the core technical knowledge about mechanical engineering. Okay, like the strength of materials, engineering, mechanics. Okay, so these are the things which are required, and you should ideally, you should ideally know what are the things which are happening, right? So again, we will starting. So the contents for today's webinar are prerequisites for a CA engineer. Okay, so first and foremost, so what is CA engineer, significance and scopes? Okay, then application in various industries. So again, if you are learning something, so you must know, so on what are the fields which are required, right? And what are the research and developments going in that particular field. Okay, then again, there are various types of analysis, so like linear and non-linear analysis, so which we are going to cover. Then meshing, boundary conditions, constraints, loads, and at the end we will have a software demo and validation for the frontal crash. Okay, so then, so like prerequisites for a CA engineer. So as I said, engineering basics, so like applied engineering, mechanics, degree of freedom, rigid body motion, friction. Okay, so these are the all the things which ideally you should have. Okay, then other than this, so like strength of material knowledge, so like types of stresses and strains, material properties, curves, beams, shear force diagram, bending moment diagram. Okay, so these are all the things which are required. So mechanics of materials are actually, and engineering mechanics, these two things are actually core ethics. And again, so you must have slight knowledge about finite element analysis, like what are the types of elements used. Okay, definitions, element types, stiffnesses. Okay, then, so first and foremost, so like as this is an application of FEA, this crashworthiness. So like what is FEA, right? So FEA is finite element analysis. So this is one type of an approximate method to solve any engineering problem. Okay, so first and foremost thing, so before going ahead, so what we are doing in FEA, right? And why we need the FEA, right? So as I said, so it is an approximate method, right? So why we need that approximate method? If we have that analytical methods which are formula based, or if we had that experimental methods, right? If we can do a certain experiment and can find out the results, right? So again, why that are required? So the sole reason is because, see, so analytical methods are actually formula based, and formulas can't be derived for very complex geometries, right? If you want to do a study of too many components, okay, so then exactly it is difficult, right? So that is why analytical method, which was derived on the basis of formulas which you are learning, so that was dropped. And again, so there was another approach, so that is experimental approach. So each and every individual on their level, or each and every company in their particular level can't do experiments, right? That much of costly experiments, right? So that is why experimental approach to find out any observation and then debugging the data, so that thing was also dropped. So now this approximate method comes into picture, right? So like what is happening? So see, in approximate method, finite element analysis is one type of method. So now what we are doing in basically finite element analysis is, suppose say like you can see the image over here, right? So we have a bigger geometry over here, that is the sphere. Okay, and we are dividing that sphere into smaller elements, right? So what we are doing, so that what we are dividing, that point from which we are dividing the bigger geometry into smaller geometry, is what we call as meshing. Okay, so again, we are going to capture that also. So this is a prerequisite to go ahead in any to go ahead for any study of a component or any type of study in FEA. Okay, so if you don't have a mesh, so you can't go ahead. Okay, so you must know what are the types of mesh qualities and everything, which again we are going to cover over here. Okay, so elements also have the characteristics. So what are the elements? So elements are the smaller geometries in which your bigger which is about to capture your bigger geometry. Like you can see a sphere over here, right? So that sphere over here is captured with the help of smaller elements, right? Or in simple words, I can say that it is almost like a hexagon, right? A small hexagon is covering that solid sphere right over here. So that's the thing, right? So again, the endpoints, so like there is endpoint right over here, so from where one element like this hexagonal block is connected to this hexagonal block at a point, right? So that we call it as a node. Okay, so elements connects with the characteristic points called nodes, and that lie on the circumference. Okay, or the circumference means the edges of the elements. Okay, then again, so mesh are the prerequisites. Okay, as I said, so again, see, so like as I introduced you, so in the beginning we have that in order to solve any engineering problem, there are three methods like experimental, analytical, and numerical. Okay, so analytical method is formula based, what you learned from your engineering mechanics and strength of materials. Okay, so and experimental methods are also there. Then there are numerical methods or approximate methods. So in numerical method also, as I said, finite element method is one type of method. Okay, so we have several other methods like finite difference method, finite volume method, then functional approximate method. So these are the things like variational, Rayleigh-Ridge, weighted residual, point collocation, subdomain collocation, least square method, Gailcard method. So these are all the methods so which are actually used to solve your differential equations. Okay, by a numerical approach. Okay, not by an analytical approach, which we traditionally used to learn in our core mathematics, right? So that are one thing. Okay, then in finite element analysis also, we are actually trying to find out types of differential equation and trying to solve it using numerical approach. Okay, okay, so as the name is only suggesting, so everything is based on actually your numerical mathematics. Okay, then steps in FEA. So as I said, so first and foremost thing, you must have a bigger geometry, right? And you should understand what exactly you want to find out, right? So like the physics of the problem is everything. So if you don't have the physics, so exactly it is difficult for you to analyze. Then after physics, you should have the pre-processing. So by pre-processing, what I mean, actually meshing. Okay, so meshing and boundary conditions application. Okay, so meshing is one part of pre-processing. Okay, then again you have that model setup, so boundary conditions and everything you need to set. Okay, then after that, what you need, so once you have done with this, so then you will probably ask for solutions. So once you are getting the solutions, so like what you are going to do, so then you are going to check for the results, right? So again, so in different pieces, so like it will take different types of times, so depending upon the sizes of problems and the geometries which you are using. Okay, then again post processing. So post processing is again one of the important things. So as I said you, so this is actually an approximate approach, right? So what results you are getting, so that results needs to be validated, right? So if you are able to validate those results, so then and only then exactly, so you will be able to understand, so what are the deviations from the analytical and experimental approach, right? So that are the things. So again, so why this thing, why this method is beneficial is, so you don't have to do experiments on analytics of the problem again and again, right? So once you have the proper data, so again you can match them, right? So that is the thing. Okay, so validation is one of the important factor. Okay, so then again, CAE, right? So CAE, so like significance of CAE, right? So what basically CAE is, right? So CAE is computer aided engineering. So in this actually we deal with product development. Okay, so what are the product developments which are required, right? So like what are the methods? So in what manner actually we can develop our product with a lower and lower cost and with the core ethics of engineering, right? So that are the things, right? So significance of CAE, right? So first and foremost thing, so generating the physical response of the system at any location which might not be possible in analytical approach. Okay, so what the first very first point over here says is, so like as I said you or explained you in the beginning, so like what we are doing, so like in analytical approach we have a formulas, right? But what will happen if you have a complex geometry or if you have the things which cannot be analyzed, right, with respect to formula, so then you will be stuck, right? So we don't want that, right? So what you want then you want it to be, I mean, a very smooth process, right? So you don't want to be stuck, right? So and again you don't want a very huge cost, right, in order to perform any experiment and get the data. So it's very problematic, right? If you and again the cost price is also huge, right? So we don't want that, right? So that is again one thing. Okay, then other than this, so simulations might predict the destructive or impractical load condition and failure modes, right? So simulations, as I said, so this actually simulations, so what does it predict? So it predicts it's at certain point of time, it may predict impractical loading conditions and failure modes, right? So you should always be clear with what are the boundary conditions you have to use, right? First, you should be clear with what are the mesh types you should use. So we will cover that later on in this webinar, but first and foremost, foremost thing you should understand is what type of loads you should use as a boundary condition, right? Now, suppose say like if you are using a cantilever beam, right? So in cantilever beam, what are the things you can do, right? So that are the mandatory things, right? So one part is fixed, okay, and another part is, suppose say you are applying a load at the free end, right? So that thing you can do, right? But the fact of the matter is you should understand, so what are the loads you should use, what are the loads which are being applied on the geometry, right? So for the future, I mean for the further ahead in the simulation, when I will show you the demo of this, so you will understand that what are the things which are, I mean, we are calculating, right? So like velocities we can apply, right? So depending upon what study you want to do, you can apply it to your geometry and you can get the data. And again, the validation is one of the important thing which cannot be neglected at any point. Okay. Okay, so that are the things. Okay, then simulation, calculation, and visual representation of a wide variety of a physical parameters such as stresses or temperature, enabling the designer to rapidly analyze, perform, and possibly do modifications, right? So again, as I said, you suppose say you got a data, okay, so suppose say you got a particular data, okay, you did the validation. Now what you will do with that data, right? So you, obviously, so there will be a cycle, right? So like design engineer will be there, right? So again, CFD people will be there, you will be there, right? So manufacturing engineer will be there, right? So you are going to suggest them this data that, okay, so see, these are all the changes which I did, right? And these are all the changes which ideally you should prefer into your manufacturing or in a manufacturing steps, okay, so that your designs would be better. And also, I mean, designed to also, actually it will be more effective, and design to cost ratio, so exactly it will be lower, and it will increase your product development rate. Okay, so again, so it has said that relatively low investments and rapid calculation time for most applications, right? So again, this is a very fast process, right? You are not doing any costly setups for experiments. Again, it is not that you are again applying or trying to find out or trying to develop the formulas for very complex geometries, right? Or very complex setups, right? So exactly, so this is actually say a low cost and effective method. Okay, so that is one thing. Okay, then again, so as I said, so when you are learning something like computer aided engineering, so you should understand what are the benefits of the same, right? What are the applications, right? What are the research and development of the same is going on in a particular field, right? So like CAE, so like computer aided engineering, so it is used in various types of applications. Okay. My bad, the slide was lost. Sorry. So like, yeah, so CA in various industries, right? So again, so there are various types of industries. So as I said, so like they are used in manufacturing, they are used in different types of research and development. Okay, so there are variety of phases. So in product development where they are used. Okay, and again, as they are cost effective, so again they are better. Okay, and again the analysis of the results. So different industries have different formats to analyze the results what they are getting from the simulations. Okay, so like the one over here shown is the mode flow simulation using mode flow software, right? So there are different types of softwares for the same, right? So like there is ANSYS, then there is Hypermesh, right? Then there is Abacus, right? So there are many types of softwares, right? So for doing a particular simulation. Okay, and then CA in various industries, like in automotive industries, where exactly it is used, right? So it is used mainly for crashworthiness, right? So so like what we are doing in crashworthiness, right? So suppose say like in a crashworthiness, car body is crashing, right? So now if you have the basics of engineering mechanics, so you can easily understand that if you are going to make the basic outer structure of your automotive simply rigid, so what will happen? So suppose say like energy, so by the basic principle of law of conservation of energy, so once the crash is happening, so what will exactly be happened? So that energy will not be dissipated, right? If your car body is simply rigid, right? So that kinetic energy needs to be transferred inside, right? So in what manner it can be transferred, right? So that exactly leads to the passenger safety, okay, who is sitting inside the passenger compartment. Okay, so that study actually we are trying to capture over here in the crashworthiness study. Okay, so again over here you can see frequency response of the chassis, right? So again, so like what is happening? So in an automobile there are n number of components. Okay, they are imparting different types of vibrations, right? Like your force vibration is there, right? So what are the types of studies you can do, right? So what frequency would be more fatal, right, for the chassis, right? So that all studies needed to be done prior to once your car body is going out into the market, right? So you should understand that, right? So if you are not understanding that, that means you will not be able to develop a product, right, which will be like which will provide resistance to the frequency for a longer period of time, right? So none of the products ever provide it forever, but still, so people are trying to, I mean, have a component of chassis, like they should not provide that much of they should not fail that much of easily, right, with respect to forced vibration, right? So that are the things. Okay, so for that exactly people have done frequency analysis, then again they have done model harmonic. There are n number of analysis which people have done. Okay, so again you can see like the frequency versus pressure graphs, right? So there are n number of things which we can learn over here. Okay, then going ahead, so this CAE, so like this crashworthiness things, again, they are used in CAE departments, again in aircrafts as well. Okay, so so what we do in aircrafts actually, so we try to find out what are the structural integrity of an aircraft is, right? How much resistance it can give, right? So again that helps us while it is in air, and again it helps us, so like again it helps us in various other domains, like you can learn about, so in what are the manners you can arrange these structures, outer structures of the aircraft, right? So that are the things which will help you ideally, right? So that are the things which we try to do, right? And again, so last but not the least, so when you are developing anything, the main thing in product development life cycle is, so how much safer it is, right? So we all have heard about the Tesla model, right? The recent model which they have released in the market, right? So this is safer, right? And again it is being sold, right? So why that is so? Because it is safer, right? The safety ratings which that model has got, so it is very good, right, compared to any other car companies, right? So that are the things. Okay, so that same thing applies even in your aircraft industries. Okay, even in the rear transport vehicles, right? So that are the things. Okay, then so again going ahead, so like what are the types of analysis, right? So we should understand that while analyzing anything, so there are n number of analysis you can do using FEA, right? So like static, dynamic, right? So linear, static, non-linear, static. So first and foremost thing, so what is static and what is dynamic? So static and dynamics are actually response of your structure with respect to the loads which you are applying, or the boundary conditions which you are applying. If that response is independent of time, then we call it as a static analysis. And if that response is dependent on time, then we call it as a dynamic analysis. Okay, so that is one thing. Okay, so then again within analysis, static and dynamic analysis, we have non-linear static and linear static analysis. Okay, and then again over there in dynamic, we have linear dynamic and non-linear dynamic analysis. Okay, so like the term linear and non-linear, so it makes more easier for easier for an analyst or any mechanical engineer or a research scientist to understand what are the behaviors, right? So like if I say static linear and if I say static non-linear, if I say dynamic linear and dynamic non-linear, so what are the difference, right? So that you should understand. Okay, so that again depends upon the behavior of your geometry, right? Like suppose say what type of loadings you are giving, be dependent upon what type of material it is made up of, what are the contacts possibilities and joints which it is having, what are its degree of freedoms, right? So depending upon that exactly it is decided. Okay, so again, so So static and dynamic, static and dynamic response, so they are decided on the basis of what studies you are doing, right? So same geometry can at a particular load, if you are interested more in static study, so you can do a static study for the same. And again, if you are interested on a dynamic study, so again for that you can do a dynamic study. But usually when static and dynamic both studies are there, people prefer dynamic studies more because they are more fatal in case of your, if you're trying to do any crashworthiness study, right? So that is one thing. Okay. And then linear analysis, right? So in linear analysis, so what happens? So in terms of your material, if you speak, so linear analysis means exactly. So I hope every one of you have gone through your strength of materials, right? In your college days, right? Or I mean, like over right now, right? So you must have gone through engineering stress versus engineering strain graph, right? So over there, the graph, so what happens up to elastic zone, exactly that graph is almost a straight line, right? After elastic zone, once it crosses your yield point and it reaches the plastic zone, so what happens after lower yield point? It reaches the plastic zone, right? So exactly, then after that, exactly, so it no more becomes linear, right? Linear in mathematical terms means it is indicating a straight line. Okay. So that is one thing, right? So what happens? So like, I mean, what is the thing which we are trying to study, right? In linear analysis. So again, so what is happening, right? So like in a linear analysis, like you can see a cantilever over here, right? So what we are doing, right? So in linear analysis, exactly. So there is no point of having a contact, right? So again, what I mean by contact is, suppose say there are two bodies, okay, they are touching each other. Okay, now suppose say that contact study will not be useful in case of linear analysis. Okay, like suppose say in cantilever beam, so in cantilever beam, what ideally or traditionally we used to do, so in traditional method, so in cantilever beam we used to fix one end and we used to apply the load at the other end, right? Pointed load, right? In certain complex cases you can also apply uniformly varying load or uniformly distributed load. Okay, so there are n number of things which you can do, right? So again, so what is happening, right? So like you have to understand that, right? So suppose say like you are pretty much sure that, okay, so the amount of load which you are applying, so like depending upon the values, the material parameters of cantilever, so you can say that, okay, so it will be under elastic zone. Okay, so then exactly you should go for a linear study. Okay, then so again, so like as I said, so solver follows the straight line throughout the elastic region, right? The force versus displacement graph will vary linearly. Okay, so there will be no points of defining contacts in linear analysis. Okay, so that is one thing. Okay, then going ahead in non-linear analysis, so again see, so linear analysis and non-linear analysis. So in non-linear analysis, it is just opposite of your linear. Okay, so in linear, exactly, you are having a straight line, right, between engineering stress and strain, right? But over here, exactly, it is just the opposite. Okay, so that straight line thing is not there. Okay, so again the studies become difficult, right? So again, so if it is not a straight line, then again the second question which traditionally comes to anyone's mind is, so like why that is not a straight line, right? Because of three particular reasons. One is it has reached like material non-linearity, that means it has reached the plastic zone. Okay, the second is like it has reached the geometric non-linearity. So what I mean by geometric non-linearity is, suppose say in a geometry you have applied a load such that with respect to that, exactly in a lesser time it has it has got a very huge deformation, right? So then what happens? So in a lesser time it has got a huge deformation, right? So exactly because of that huge deformation in a lesser instant of time, it has reached ultimately the plastic zone, right? So that is what we call it as a geometric nonlinearity. Okay, then contact nonlinearity is there, right? So depending upon your contacts, okay, so like what are the things which are happening, right? So context nonlinearity is that. Okay, so again within material nonlinearity we have again seen that beyond elastic limits, so what happens? So like exactly beyond elastic limits, so like your metals become plastic, right? For non-metals within elastic limit only it is plastic, right? So again, if you are having a constant load, so a creeps are developed, right? So that is one thing. Okay, okay, so these three are actually the types of your non-linearities. Okay, So again, non-linear analysis. So again, what is non-linear analysis, right? So in a non-linear analysis, so what happens? A non-linear relation will hold between your forces and displacements, which you will see with respect to time, right? So crashworthiness exactly is a non-linear dynamic analysis. Okay. So again, why I am calling it as a dynamic, because see, in crashworthiness, what happens? So all the crashes which are happening in a car, so they are happening in a couple of seconds, right? All the failures and everything, damages, everything, they are happening in a couple of seconds, right? So indirectly, what it is indicating you. So from the basic outcome of the problem, you can understand that, okay, so everything over here is time dependent, right? Like over here, you can see this animation, right? So everything over here, the stresses, strains, and everything which are developed over here, so they are dependent upon time, right? So that is why it is a no. And again, why non-linear? Because non-linear, because what happens? So there is a sudden deformation in a very less amount of time, right? And again, depending upon, again, so like car component is not made up of one material, right? There are different types of materials applied to different types of components, right? And you are doing collectively the study of this entire BIW, right? So by BIW, what I mean, body in white, right? That is the outer structure of your automotive. Okay. So again, as I said, so these are the so what happens? So like if force versus displacement plot, so if if they are not in a straight line manner, so what will happen? So there will be a stiffness, right? So F equals to minus kx, right? That stiffness only acts as that stiffness only provides resistance to the deformation, right? So that is one thing, right? So if that force versus displacement plot is not a straight line, so in case of your finite element analysis, so each and every element will have a different types of stiffnesses, right? Stiffness matrix, right? Because see, there will be n nodes. Each and every node will have a particular stiffness at different loading conditions, right? So there will ultimately be a stiffness matrix which will be developed, right? So which will not be actually constant during the loading application. Okay, now you can see, like as I said you, so there are three types of non-linearities, like geometric non-linearity, like geometry will undergo large deformations, right? Then stresses, strains, so material non-linearity is there. So actually, so like it reaches the plastic zone. Then contact non-linearity is there, that is change in contact status, right? So overall, what is happening? So over here in crashworthiness, if you go with respect to contact non-linearity, you can understand that at the start, so like all the components of a car, they are together, right? So there was a constant contact, right? Now, once this body is crashing, so what is happening? The status in the components with respect to one another, so that contact status is changing, right? So that is one thing, right? So with respect to that, exactly, you can say that, okay, contact non-linearity is also there, right? So now why we are doing this study, right? For the frontal crash. So that is again one more important question, which ideally anyone should understand. So we are doing this because we want to make sure that anyone who is sitting in the passenger compartment, so how much safety for him is exactly being obtained, right? So there are certain parameters depending upon which we can say that, right? So those parameters, so as I said you, so in the beginning, so as I asked you for one question, like, yeah, so like what is happening? So if you have read about the engineering mechanics or any basic level physics, right? So you must have understood the law of enough energy conservation, right? So suppose say if a car is moving ahead, okay, and it is crashing on a rigid wall. Okay, suppose say that car body is entirely rigid. Okay, so by rigid, what I mean, so that no deformation is allowed. Okay, so you can only do the study of mechanics. That is, you can only do the study of motions, right? Now, suppose say if that car is crashing on a rigid wall, okay, so if it is not deformable, so where will all the kinetic energy go? So if some of you will say that, okay, so it will go in a friction. Okay, so then exactly, so if it goes to a friction, okay, so how much energy will be lost, right? So frictional energy, so exactly it will be lesser, right? It will be not that much, right? Right. So that is the one thing, right? So exactly we need to lose that energy, because if that energy remains like that, any guy or any of the individuals who is sitting on the passenger compartment, it will be fatal for him, right? Because see, if car body is not deforming, so now who can be deformed? It is obvious that if any individual is sitting on the car, so obviously our human body is not rigid, right? So it is deformable, right? So it will be directly transferred as a stress wave to any of the individuals who is sitting inside the car, right? So it will be fatal for him, right? So that is why now what people have come up with. So people have come up with the BIW, or the outer car body, to be flexible. Okay. Now that flexibility should not be also too much. Okay. If that is too much, so what will happen? So like suppose say like you are sitting on a car, okay, which is made up of say a very deformable material like sponge. So what will happen? So it will simply crush you, right? So we don't want that also, right? So then exactly what people have done is, so like in the research and development, so Crashworthiness Industries, so what they have done is, so they have developed the they have allowed certain deformity in the BIW outer structure, such that it is deformed, and the potential energy of the shape deformation, so that is exactly balancing the kinetic energy, okay, such that the passenger who is inside is safer. Okay. Now on what basis we can say that, right? So that thing again we are going to see. Okay, I will show you the demo for frontal crash. So there I will try to explain you. Okay, so like what we are trying to do, right? So on that basis exactly we are trying to find out, right? So exactly that is the thing. Okay. Then overview of crashworthiness, right? So what is crashworthiness, right? So as I explained you, okay, so crashworthiness is the ability of a structure to protect its occupants during an impact. Okay, this is commonly tested when investigating the safety of an aircraft and vehicles. Depending on the nature of the impact and vehicles involved, the different criteria are used to determine the crashworthiness of a structure. Okay, now suppose say like for a automobile, so the safety criteria may be different, right? Now you are using aircraft, so it's different. Now suppose say you are using any transport vehicle like your bigger say suppose 12-wheeler or 20-wheeler trucks, right? So exactly that would be different, right? So that criteria are different with respect to vehicles. Okay. And again with respect to crashes. Okay, so like over here you can see that, suppose say like, I mean, a passenger is outside the car. Okay, so he's colliding with the car, right? So what are the criteria which can happen, right? Again over here you can see this car body is crashing on a wall, right? So what are the criteria which can be seen, right? So again suppose say like you are having a frontal crash, but that wall, instead of being planar, so like it is slightly in the forward position, right? So what is the thing, right? And again depending upon the velocity of your car body, right? So again these things also vary, right? Like suppose say for 50 km/h the crash worthiness results, so they will be different for the car, obviously for the car with a velocity of 64 km/h, right? So that is the thing. Okay. So actually we are dealing with the crash worthiness. So actually we are dealing with the crash worthiness study to find out the safety of an occupant who is sitting inside. Okay. And again, this crash worthiness thing is applicable for rear crash. That is, if it is crashing from the back side or side, right? Or side or from the sidewards, right? Or again, suppose say like this car is over here and another vehicle is coming and striking it, right? So what are the safeties, right? So different kinds of studies are being analyzed, okay, together and collaborated once before the any BIW is taken for research and development of your car body. Okay. Then ultimately it leads to the total development of your cycle, okay, on which exactly the product should be. Okay. Then exactly as I said you, so major thing in FEA is, so like first and foremost thing, you should be covering all the bigger geometries with the smaller elements, right? That is what we call as a meshing, right? So now what is meshing, right? So finite element method. So like, see, so suppose say this is a bigger geometry. Okay. Now suppose say you are trying to capture this geometry with infinite number of small cells. Okay. Like consider an example of cells capturing your entire body, right? Outer skin, right? So what happens? So like if you try to do study like that, so there will be infinite number of cells, right? By infinite, what I mean, it is very difficult to calculate, right? So what we are trying to do, so we are trying to make it from infinite to finite, okay, with the help of discretization or meshing of nodes and elements. So one of the purpose of meshing is to make the problem solvable. Okay. If it is not solvable, okay, so then exactly it will be difficult. Okay. So by meshing, you can break the bigger domain into pieces. As I said, so you have a bigger geometry. You are trying to break that bigger geometry into smaller geometries. Okay, so why you are doing so? That will ease you. Okay, so how that will ease you is, so it will ease you in creating a stiffness matrix, right? And depending upon that stiffness matrix, exactly. So as it happens, so like in any of the mechanics book, so you have gone through. So like, so what happens? So the internal force is equal to negative of stiffness times x, right? So same thing applies over here in case of elements also, but the fact of the matter is, so you are using the stiffness of an element, okay, and that element is having 2-3 nodes, okay. Like suppose say if you consider 1D beam, okay, so in 1D beam what happens? So like you have that 1D element and it is having suppose say 2 nodes, okay. So like wait, just give me 1 minute, okay, I will share it, okay. I hope my screen is visible, guys. So like suppose say like you are having this 1D beam, okay, so by 1D what I mean, suppose say you are having an element, okay, so which is like a line, okay, 1D, okay. So why we are calling it as a 1D is because it has only one dimension, which we call it as a length by which you can identify it, okay. Okay, so then what happens? So in 1D beam, exactly, you have the 2 points, right, over here, the end points, right, here and here, right? So this 1D 2-noded beam element, so like depending upon the points, exactly, you have a stiffness matrix, right? So that stiffness matrix for 1D beam element, so like how exactly it varies, right? So you have to derive that stiffness matrix, okay. So like what we used to do, right? So we traditionally, so what we used to do, so in case of say suppose like normal stresses, suppose say you have say suppose this one, okay, this 1D beam, you are applying a force like this, okay. So what happens? So like suppose say stress, so by Hooke's law, okay, what we have, so by Hooke's law, so Hooke's law is a traditional law which we use, okay, so according to which stress is directly proportional to strain up to elastic limit, right? Or stress is equal to Young's modulus times the strain, right? Now stress was what? So stress was your force per unit area, right? And your Young's modulus is, suppose say let this be y, okay. And your strain is what? Yeah, so engineering strain is actually your change in dimension by initial dimension, right? Right, so like suppose say delta L by L, okay. So now suppose say f was equal to kx, right? Now suppose say if I want to represent f over here, how I can represent from this equation? So I can represent it using f equals to ya delta L by L, right? Now ya by L, so can you able to, I mean, understand that f equals to kx, so that thing you can put it over here, right? Where x was what? So x was your displacement, right? Or over here in terms of your elements, you can call it as a deformation, right? So that thing you can put it as x, right? Now this becomes actually your stiffness, right? So that stiffness was there when? So that stiffness was there when? So when you are supposed to fixing this one node and you are applying the force at the other node, okay? An external force at the other node, okay? So that stiffness matrix was there over there then only, right? But now in case of 1D beam elements, exactly, you are having 2 nodes, right? So now you need to find out the stiffness for all these 2 nodes at different cases. By different cases, what I mean is, so once you fix this node and you apply the force at this node, then you fix this node and you apply the force at this node. So what you will find out is a global stiffness matrix, okay? So that stiffness matrix for one particular node, so how exactly it will be? So it will be like YAL. Okay. So this is the stiffness matrix ideally which you will be getting for 1D beam. Okay. Now try to analyze this thing with the help of 2D, right? So these things is becoming complex for 1D, right? Now if you go with 2D and 3D, right, with any traditional finite element books, so you will be able to understand that this stiffness matrix is there for one element, right? Now there are suppose say like if you are trying to study any car body or BIW, there are n components, and within that n components, if suppose say like there are 40 or 50 elements, so there will be a very huge matrix, right? So that matrix calculation is made, right? And linearity and non-linearity actually hampers your study over here in stiffness. Okay, so that is one thing. Okay, so that I try to explain you with the help of 1D beam actually. Okay, now again going ahead, so again like that are the things which are being calculated. Okay, so again, so see, so like as I said, so in 1D beam, why we are calling it as a 1D? Because of length, right? And again, if with respect to degree of freedom, so in 1D beam, what you have, so suppose say again going back over here, so in 1D beam exactly you have only 1 degree of freedom, right? So either it can move like this or it can move like this, right? I mean, it can only elongate, right? You can't say that, okay, so it will have some lateral deformation, right? Because lateral dimensions are actually negligible, right? Okay, so that means it will have only 1 degree of freedom, right? So there are two ways in which you can call it, right? So that is one thing. Okay. Then again, going ahead, so like meshing is an important thing. So factors deciding the mesh type, right? So again, what type of mesh to use, right? So see, like 1D elements are there, then 2D elements are there, which captures your rectangle and rectangles, I mean quads, okay, in engineering terms, and trias, right? Or triangles, right? So, and again for 3D, you have that hexa elements, right? Tetra elements, right? So what type of elements to use, right? So that is again one thing important, which ideally we should understand, okay? Okay, so then how you can understand is, so like, see, depending upon the size and shape of the model, right? Depending upon the element qualities, right? So you can understand, right? So like, suppose say for size and shape of the model, so simple geometries obviously go with quad elements, right? Complex geometries goes with tri elements, right? For structural and fatigue analysis, we go with quad elements. For casting analysis, we go with tri elements. For crash studies, like over here, we obviously go with mixed elements, right? So by mixed, what I mean, so it will have quads, trias, okay? So again, so like so there are things, right? What type of analysis you are doing, size and shape of the model, right? And again, time to finish the task. Okay, so simulation, right? So suppose say like for sufficient available time, manual meshing with hexa elements gives you more accurate results, right? Now suppose say you don't have the sufficient time, right? So then what you can do, so in hexa, actually, in suppose say like consider a hexa elements. Okay, so like by hexa, what I mean, so like suppose say you are having a cube. Okay, so it is having 8 points, right? Or 8 nodes, right? Now suppose say if you are having a tetra, so what will happen? So that points will be decreased, right? So again, exactly, if the points are decreased, so that stiffness matrix size will be decreased, right? And exactly, it will take lesser time, right? So depending upon your time, what you want the simulation to finish, what type of analysis you are doing, size and shape of the model. Okay, so these are all the three factors on which your mesh element type varies. Okay, then significance of mesh, right? So mesh influences your results to a very larger extent. Okay, so whether while in time of solving, or while in time of speeding up the simulation, or while in time of checking or validating your results with analytical or experimental data. Okay. Okay, so that is the thing. Okay. So as I said, so in this process, so continuous geometric spaces of an object is broken down into thousands of one or more elements properly to define the physical shape of an object. Okay, so simply put, a good quality mesh equals to more precise results. Okay, so suppose say like if your mesh is more accurate, the mesh flow is more accurate. Okay, there is no breakage in your mesh flow. So obviously your results will be more accurate with respect to your analytical and experimental methods. Okay. And again, if it is not accurate, and if there is too much of breakage in mesh flow, okay, it is not that what with the analysis type you should go with the mesh flow. So obviously you are going to get a results, or obviously it may happen that your solver fails while calculating a result. So but in both the ways, exactly, so you will not be getting anything. Okay, so that is the thing. Okay, so ideally in this process, okay, so you should traditionally go with the mesh quality. Okay, So again, boundary conditions or loadings, right? So what are the boundary conditions you should use? Okay. So as I said, so you should understand the physics of the problem. So that physics of the problem considers your boundary conditions. Okay. Boundary conditions. So what are the things which is happening, right? So in 1D beam, as I said, you, so like suppose say if we are having that elongation, so it's fine. So you can, so like you can apply that, suppose say like a axial load, right? Let it be tensile or let it be compressive, right? So you can do that, right? Again, suppose say if you want to do bending studies, so then you should apply the shear force, right? So depending upon that, exactly, we are trying to calculate the results. Okay. Then the information about the so in boundary conditions, what we are doing, so there are two types of boundary conditions. Okay, so one is your essential boundary conditions and another is your non-essential boundary conditions. Okay, so like suppose say by essential thing, what I mean is, so suppose say like you are having that cantilever beam. Okay, so now in cantilever beam, what happens? You are fixing one side and you are making the other side free. Okay, so then exactly what will happen? So suppose say like that fixed support, without that fixed support, you can't call it as a cantilever, right? Like suppose say if you are not fixing one side, so without fixing, you can't call it as a cantilever, right? That is one thing, right? So over here, suppose say like if you apply a load of say 10 Newton, okay, so over here, what are the constraints to this particular say cantilever? So there are two constraints. One is this fixed support Fs, and another is your force, right, which you are applying. Now suppose say whether that force and that fixed support, so like with respect to whom exactly you can call cantilever. See, if force is not there, if one side is fixed and one side is free, again you can call it as a cantilever, right? So that is the important thing, without which your geometry will not exist as a cantilever in itself, right? So that is the thing. Okay, so then this becomes your essential boundary condition and this becomes your non-essential boundary condition. Now suppose say another guy came in, he said that okay, I will not apply force, rather I will apply the displacement, right? So you are free to apply anything, right? Displacement, velocity, but the fact is you can't replace this fixed support with anything else, right? Okay, so then this becomes your natural boundary condition. Okay, and this becomes your essential boundary condition. Okay, then again going ahead. So essential boundary conditions are the one without which the system cannot exist in equilibrium condition, that is stable condition. Non-essential boundary conditions are the ones where loads or temperatures are being applied. Now suppose they consider this beam. Okay, so there like there is one more example which I would try to give you. Okay, so like suppose say you are having an axial load, okay, along F. Okay, so you are having two nodes, okay, one and two. Okay, now suppose say the point one is fixed, right? So why that is fixed? Now suppose say suppose say any other individual came in, he said that no, that's the I can substitute it, right? So suppose say you try to substitute it. Okay, and as a substitution you just remove the fixed support. Now what will happen due to the mechanics? So what will happen? This force will simply, I mean, move this beam down, right? So there will be a motion, right? This beam will not be fixed and you will not able to do the study, right? So this fixed support indirectly what it is doing, so it is applying the stable equilibrium in terms of your motion, right? So that is one thing, right? The force that is applied at node 2 is actually your natural boundary conditions, which create slight deformation, will not affect the stability of the rod, right, with respect to equilibrium. Okay, so this is another thing. Okay, then again, so like before going ahead, so like I would like to show you, so the 2-3 things, like so we have tried to solve the problems of your basic frontal crash. Okay, so like these are the things which we tried to find out. Okay, so like your von Mises stress, intrusions. So what are intrusions, right? So wait, I will try to show you that. I hope my screen is visible, guys. So what we are doing is, so we are taking a basic BIW of a car, okay, the frontal part, and then after that, what we are trying to do is, so then after that, we are trying to find out, like what are the changes which are happening, right? So there are n number of cards over here, okay. So as I said you, so while solving any FEA problem, you should understand, so like what are the boundary conditions, what are the meshes, and what are the things which we should use. So traditionally, while solving over here in Skill-Lync, we try to solve a problem with the radius solver in hypermesh. Okay. So any crashworthiness problem. Okay. So what we have done is, so like we have we have applied a rigid wall. Okay. And then ultimately what we have done is, so we have applied the velocity to this car body. Okay, and it is ultimately crashing into this rigid wall. Okay, and we are trying to find out the results. So by results, what I mean is, so by results I mean what are the von Mises stress which are generated depending upon your von Mises theory of failure, right? Then again, what are the deformations which are happening into the passenger compartment, in which actually the driver will be sitting and any other guy will be sitting, right? So what I mean by intrusion is, by intrusion I mean that what are the deformations which are traditionally happening, right? So that thing we should understand, right? So like how much deformation is expectable, right? So for that we have different standards, right? So there are certain necessary cards and everything which you will learn once you opt for this course. Okay, then again rigid wall is there, right? So then again there are various types of natural and local coordinates, right? There are various types of outputs, like you can see the local coordinates, right? XYZ over here, right, at different parts. So why I have done so, because I want to calculate the results at that particular component, right? So suppose if a crash is happening, I should do a study at the multiple points, right? Then and only then I would be able to understand that what are the forces which are generated, what are the deformations which are generated, and how much deformation is actually happening into this passenger compartment, so that any guy who is driving, who is operating this vehicle or inside this vehicle would be safer in case of any crash, right? And then exactly I can check with respect to FMVS, Federal Motor Vehicle Safety Standards, right? Right. So that are the things, right? So again, going ahead, so like we will try to show you the simulation as well. Okay, sorry. So like, yeah, so wait. So like before the start, so like you can see over here that so the von Mises stress which are generated, right? So at the start, exactly it is showing, so with the help of this violet color, it is showing that it is almost zero, right? Now once the start, now once exactly, so the BIW is crashing. So what is happening? So you can see that results are generated, right? So that is one thing. Okay. Okay. Okay, so that is one thing. Then other than this, so like, so here you can see the stresses values, right? So it is in MPa, right? So what are the stresses which are generated once it is crashing, right? So this is about your von Mises stress. Then other than this, we have also talked about your energy plots and intrusion, right? So wait, we will show that also, right? So over here you can see like the, so what are the sectional forces which are generated, right? So I tried to explain you. Okay, so what are the sectional forces which are generated once we are going ahead, right? So these all the forces are in Newton, right? So like suppose say there are different components, right? Like suppose say left rail, a left A pillar, right A pillar, left B pillar, right rail. Okay, so there are different components. So with respect to that, exactly what are the forces which are generated into a cross section, which is plotted with respect to your local coordinate system. Okay, so that is one thing. Okay, so what are the forces being generated? We are trying to do the study and we are trying to find out what are the components which will have the maximum force, so that we will apply the material of such a kind to them, and also we will try to make the geometry in such a way that it also provides you the geometrical rigidity, right? Or area moment of inertia should be higher at that particular component. Okay, so that is one thing. Then other than this, so like we have also plotted for your energies, right? So what are the energies which are occurring, right? So like over here you can see the total energies, right? So like total energy is almost constant, right? So why that is so? Because ultimately while crash, what is happening? So that kinetic energy which was there, okay, so it is actually, so over here you can see a drop in kinetic energy, right? So that is because, so kinetic energy is ultimately trying to reach zero, right? And your elastic energy is also trying to increase, right? That in that manner, actually what will happen, so that deformation energy will take over your kinetic energy. With respect to, there will be also certain losses, okay, by the law of nature, but actually in that manner the energies will be lost, and exactly that will actually help the passenger to be safer, right? So that is one thing. Okay, so then we are doing the energy level studies, right? Then other than this, so what we are trying to do, so then we are trying to find out the elongation, right? So suppose, say, like over here you can see, like we have plotted two springs, right, at the passenger compartment. Okay, so your car body is moving with a velocity of, say, 15 meter per second, right? So then exactly what are the deformations which are happening into the passenger compartment, right? So that you can calculate, right? So there are different methods to calculate the same, right? So that is one thing, right? So we are trying to calculate them using various types of elements, various types of local coordinate systems, right? So again, there are n number of things which you can traditionally do, right? So why we are trying to calculate the same is, I hope I have explained, right? So that your passenger would be safer, right? If you have the data that how much deformation is happening with respect to a particular velocity, so what you will next do is you will try to make your product in such a manner that the deformation will be within that expectable range, and after that exactly it should not cross a limit, right? So if it crosses a limit, so that will be more fatal, right? And again, you can, for structural rigidity, you can apply more thicknesses to your BIW, right? Also, you can increase the area moment of inertia, right? You can use different materials, right? So that are the things on the basis of which your exactly crashworthiness industries used to function. Okay, they used to provide you the data and everything. Okay, and again, there are standards, right? So for everything we have standards. So same is there in case of crashworthiness, right? So for frontal crash, we have different FMVSS standard, right? Okay. Okay, so this is actually the demo. Okay, so then again, so like there are n number of methods in which you can do this thing. But again, so crashworthiness study becomes useful. Again, we are plotting the cross sections, right? So like suppose if you go over here in A pillar, you can see a cross section, right? Because I want to find out what are the axial forces which are generated into this A pillar. So this thing over here is actually your A pillar. Okay, this is your B pillar. Okay, so these are the things. Okay, so okay, then again going ahead, so like these are the things which we tried to find out. Okay, so material and properties, right? So material and properties, so like what are the materials we have used, right? So like over here you can find out, right? So there are n number of components. So different components have different types of materials, different types of laws on basis of which we are working in. Okay, so if you so like Hooke's law is the beginning. Then other than that, there are an n number of laws. Okay, for plasticity, we have different laws for different components with respect to different points of application. Okay, then again going ahead, so like over here you can see that this is your actual boundary condition, right, where we applied the velocity, right? Okay, then other than this, so what we did, so we also created one rigid wall, right? So these are the things which we did traditionally, right? Okay, and these are the sections which we traditionally created, and we finally found out the forces in that. Okay, then other than this, so like that was all. I guess it was all about the same. Okay, so like other than this, so like if you want to opt more for crashworthiness studies, so you can watch the standards, right? So there are FMPS standards, right? Again, you can opt for our course. Okay, so that are the few things which traditionally you can go ahead with. Okay, all right. So so that is all from my side.